I will continue with the tight binding model that I was discussing in the previous lecture. So, in the previous lecture what we actually considered was tight binding model involving just one orbital per site. With one orbital per site is what we were considering, but very often when you have transition metal ions, then you will be having the 3d, the 4s and the 4p, they are all close in energy. So, there will be overlapping of these 3d, 4s and 4p bands. So, you really need to consider more orbitals. So, for example, whenever you have transition metal ions, you have 3d, 4s, 4p for the first row, which are important. So, in this case what happens is you have to consider all these orbitals together in order to construct the tight binding Hamiltonian matrix and also obtain the eigenvalues for the tight binding Hamiltonian matrix. And how does one go about doing that? Is pretty simple. So, let us assume the orbital index is m. For example, in the case of if you are looking at 3d, 4s and 4p orbitals, you have 5d orbitals, 1s orbital and 3p orbitals. So, altogether m will go from 1 to 9, and then I can write down for each m, I can write down a tight binding wave function with a given wave vector psi m k of r as a normalization constant 1 upon root n times sigma over n e to the power I k dot r n u m r minus r n, where capital R n are the lattice sites at which the atoms are located and m goes from 1 to 9. Now, in this particular case I can construct a trial function which is given by phi of k, similar to what one does always in the variational method. This I can write it as sigma over m prime c m prime psi m prime k of r. So, you can now set up the Hamiltonian matrix. The Hamiltonian matrix is given by, that is actually what you are trying to do is minimize the energy expectation value, which is equal to phi k h phi k divided by phi k and minimize this quantity, minimize E with respect to cm prime. So, let us see how it will look like. It is quite simple. First I have to find out what is psi k h psi k look like. Psi k h psi k prime, how it will look like. This also has a band index. So, let me also put the band index. And I made a mistake before. The value of k is the same because in energy band theory k is conserved. So, because of that k does not vary when you take the Hamiltonian matrix element for different k values is 0. So, this is given by, I will call this h m k m prime k, and this is equal to 1 upon n. So, just as before, sigma over n prime e to the power I k dot r n minus r n prime times u m star r minus r n h u m r minus r n prime d cubed r. So, this is what we are going to be getting, and let us see, we will simplify this a little more just as we did before, and this becomes, I have the Hamiltonian is equal to H naught plus sigma over n not equal to 0 V r minus r n. So, if I put this into the Hamiltonian to the matrix element, I will get the following: psi m k h psi m prime k is then given by 1 upon n sigma over n comma n prime e to the I k dot r n minus r n prime is I k dot r n minus r n prime, and then I will have integral u m star r minus r n and then I can write here as h naught plus sigma over n double prime not equal to 0 v of r minus r n double prime times u m r minus r n prime d cubed r. So, right now I am only computing the numerator, and I will compute the denominator later on, which is very trivial once you compute the numerator. This quantity that I have here that will give me E m, and this has to be m prime. So, that will give me E m times delta m m prime plus sigma over n prime not equal to 0. I will put the prime or whatever that correctly afterwards. So, I will have e to the minus I k dot r n integral u m star r minus r n u m prime r d cubed r. This whole thing must be multiplied by E m, because I am going to put the first term and then I will have the whole thing, and I have taken care of the fact that when I have two indices n and n prime and I am summing over both of them, then one of the summation of the over one index will give me n, which cancels against the n here. So, one of the indices go away and I only have another index, and that will be n not equal to 0 of this quantity plus sigma over n prime not equal to 0 and sigma over n. I will have e to the power minus I k dot r n times integral u m star r minus r n times v of r minus r n prime u m prime of r d cubed r, and I just, so these are the terms that I will get. So, as we see, the first term comes from just h naught part, the first term comes just from h naught part, and the second term comes from the interaction part. And as before, we will again do the two center approximation. So, if we do the two center approximation, then this whole thing will get simplified, and what we will have is the following. In order to define that, we will have to define certain integrals. So, let me define some integrals which are j m m prime, which is the interaction integral, Now this is at positions Rn comma Rn prime. So this actually I am still retaining the 3 center integral and all the multi-center integrals, in fact 2 and 3 center integrals both. So I will have um star r minus Rn v r minus Rn prime prime r d cubed r. So this we can either do a 2 center approximation if we want, or we can just keep it as such and calculate the 3 center integrals also. The other integral is the Coulomb attraction integral, or the crystal field integral as it was called, and the crystal field integral can be represented as k prime, which is equal to sigma over all the lattice sites times integral u m star r, there will be no r minus Rn because it is interaction of the charge density with the potentials at other sites. So m of r d cubed r, and again this n will be not equal to 0 because the one that is equal to 0 goes in the E naught part, and what we have is that in terms of these I can actually define h m prime for a given k as equal to em I prime k, okay, plus k prime plus sigma over n equal to 0, sigma over n is the minus ik dot Rn times j prime Rn plus sigma over n prime not equal to 0 j prime Rn comma Rn prime. So this will be the Hamiltonian matrix element, which is a numerator, and the denominator will be the following: I prime k which is equal to delta prime plus sigma over n not equal to 0 e to the minus ik dot Rn times integral star r minus Rn 0 prime at just r d cubed r. So what we are seeing is that we have got a kind of an overlap integral here and then the energy integrals on top. So if we minimize this whole thing with respect to so what you get for E would be sigma over m prime h prime. So E of k, let me write, is h prime k cm prime divided by delta prime plus sigma over n not equal to 0 e to the ik dot Rn. This will again be sigma over m prime e to the ik dot Rn integral um. So that integral I will call just the sm prime. Sm prime r minus Rn. So if we have this, it is quite simple that minimizing just as in any variational calculations. So what we are actually doing is minimizing the expectation value of energy as a function of k with respect to the coefficients Cm, we get the equation which is simply H mm prime minus E S mm prime sigma over m prime Cm prime is equal to 0, and solution of this exists if the determinant H mm prime minus E S mm prime is equal to 0. So, this is nothing but the Cramer's rule. So, what we have to do now is to do the energy band calculation. This is of course for every value of k. So, to obtain the energy band we have to compute the matrix elements of the above matrix. The dimensionality of the matrix is actually, if I am using S, 4s, 4p and 3d orbitals, what we will have is this matrix HMM prime is a 9 by 9 matrix, and you solve this for every k in the Brillouin zone, use BSW notations and compatibility, to obtain the energy band structure. So, this is easier said than done, because what happens is that we have various kinds of integrals. Okay. So, look at the following, that is, when I am looking at J Rn prime. So, what I essentially have is the following, that is, I have the potential here which is at V of r, and then I have n here Rn and an Rn prime, and I have these orbitals something like this maybe. Okay. So, and I will have to calculate the integrals based on these functions and the potential function V of r. Well, there is a way of doing this, at least for two center integrals. In the cubic lattice, this can be done using what are called Slater-Coster rules. In the Slater-Coster rules, what one is having is the following, that is, if you have two sides A and B, then if we have orbitals S, P and D, the only interaction integrals you will have, the only interaction integrals which are unique. Which are unique are the following. VSS sigma. Okay, this corresponds to an s orbital at, again, as a function of distance. So I have an s orbital here and another s orbital here, and the distance is r, and I am having an overlap. Okay, so this is one kind of integral. So let me just write down this integral. I will not write the others. So this is nothing but 4s r v of r 4s. So let me put a star, r minus r d cubed r. So this is the integral. And if I am having p orbitals, so s and p orbitals are also going to be having only sigma overlap. VSP sigma at r is the following. Can have a plus here and then a p orbital, and this will be VSP sigma. This is A and this is B. That distance is r. Similarly, I can also have VSD sigma as a function of r. So this is nothing but I have the s orbital here, and let us say I have a dx squared minus y squared orbital or dz squared orbital, whatever you want. So this is a dz squared orbital, let us say. So this is the overlap that you will have, or the energy integral correspond to dz squared with s. And when it comes to interactions amongst the p orbitals, I can have the following: VPP sigma of r, which is given by the p orbital on one side and p orbitals are on the other side. And so this is the interaction which will be VPPP sigma. And then I can have VPP pi of r, which goes as, there is a pi orbital here and a pi p orbital here, and they have got an overlap. And this is different from the sigma orbital because you have a nodal plane passing through the internuclear axis. So if you are looking at the internuclear axis, then you have a nodal plane there. So this is the pi orbital, the pi overlap. So this is a PP pi overlap. I can also have the VPD sigma. So this can be of this type. I can have a p orbital like this, and then I can have a d orbital, and this will be PD sigma. I can have VDD sigma as a function of r. So the DD sigma will be the following. I have a d orbital, and then another d orbital, and this can be interaction between these two d orbitals via a potential is a VDD sigma r. And I can have a VDD pi interaction. The VDD pi interaction will be of this form, that is, let me take I only took VPD sigma. I can also have a VPD pi. Okay, so let me, I did not do the VPD pi. So VPD pi will be again this integral. Okay, and dd pi will be this integral which will be so these are the two centers, and this has got two nodal planes. The two nodal planes are the following. Okay, that is one nodal plane, and the other nodal plane will involve the plane is plus plus minus minus. So, that will be only one nodal plane in this case also, because there is a pi overlap. So, one nodal plane. In this case we have no nodal planes. With d orbitals you can also have another kind of overlap which is called dd delta. So, dd delta involves the following, that is, let me take a d orbital here and another d orbital here. So, you will have plus plus minus minus plus plus minus minus. So, the overlap will correspond to the following overlap. So, you will have this one, this one, this one and this one. So, what you have is internuclear axis has got two nodal planes, you see. One is this nodal plane and the other one is so there are two nodal planes, and with the VDD delta. Now, what the Slater-Coster rule says is the following. They obtained it for cubic lattices. It is possible to do it for others. It says that if R is the internuclear vector, let me draw the diagram. So, this one atom and the other atom is here, there, A, B, and you have this vector RAB. And if L, M, N are the direction cosines of RAB, so the direction cosine of this one will be LMN. So, this will be N and this will be L and this will be M. So, if this is theta, phi and gamma, then cos theta is equal to N, and then cos phi is equal to M, and cos gamma is equal to L. Now, in terms of this L, M and N, you can express in general the interactions between two centers, between orbitals on two centers. In terms of VSS sigma, VSP sigma, VSD sigma, VPP sigma, VPD sigma, VPP pi, V dd sigma, V dd pi, V dd delta. Okay, so you can in principle use this and the direction cosines LMN. I think what I will do is I will stop at this point and I will continue with the next lecture, and I will show you some typical expressions for energy of interaction between, or the interaction integral, which is involving, say for example, one of the p orbitals with a d orbital or the p orbital with s orbital and so forth. I will give you a few examples. So once you can do all these things, you can actually set up the Hamiltonian matrix and solve for the eigenvalues. I think we will discuss more of this in the next lecture, and we will meet again. Thank you very much.